Yeah, are you able to see module 4 screen? Okay. Can you see the screen?
No, sir.
Module 4 is not shared with you?
No, sir.
Okay. Now can you see? Module 4 has come?
Yes, sir.
Yes, sir.
It has come. Okay, be alert here a bit. Okay, be quick. Okay, so in module 4, what we are going to learn is the fatigue from variable amplitude loading. It's not constant amplitude, but it's a variable amplitude loading. That is, load keeps varying every cycle. So that's what the total gist, and how it will affect the fatigue life of the component is what we are going to learn. So to understand that, we need to learn about spectrum loads and cumulative damage. Okay, spectrum loads and cumulative damage quantification and concept of damage fraction we need to know. Then cumulative damage theories we need to understand. That is from Palmgren minor rule is there. Then we have cycle counting methods, which is very, very important as to how to count the cycles. Okay, that is whatever the cycles that we time stress, load stress, stress strain cycles, they are all cycles. So how do we count such cycles is what we learn out here. So moving on to that, the introduction part. Okay, so here, so when loading and unloading do not occur in constant amplitude cycles, but in a variable amplitude manner, the cumulative effect of these events may produce fatigue failure. So the term cumulative damage refers to fatigue effects of loading events other than constant amplitude cycles. That is when you have a component, so if your amplitude of loading, okay, is constant, something like this, then it is subjected to a different mode. But there are many instances in practice where the amplitude of loading will not be uniform. It will be sometimes more, sometimes less, then again more, then again less, and then less, then again it may increase, and so on, like that. So in practice, this is how the components are subjected to variable loading. Is that okay? So the term cumulative in the sense that is both constant amplitude loading and variable amplitude loading, okay, put together will produce fatigue failure. Okay, so this summation or cumulative loading cycle is called, in technically, is called a spectrum. So this is the spectrum that which consists of both the constant amplitude cycles and also the variable amplitude cycles is called a spectrum as used in fatigue literature. So that is often means series of fatigue loading events other than uniformly repeated cycles. So this is what is called as a spectrum. Yeah, are you able to understand? Are you able to understand? So that
Yes,
is
sir.
when you take accelerometers and transducers, place it near running lathe spindle, so you will get a recording of all the vibrations. Okay, or if you keep it on the lathe bed or drilling machine spindle head, right, or on a aircraft wing subjected to loading cycles, so you will get a spectrum of vibrations which come most probably which will be other than constant amplitude cycles. So that is what is called as spectrum. Did you understand what I mean, what I am telling?
Yes, sir.
Okay? Yeah? Are you able to understand?
Yes, sir. Yes, sir.
Okay, so cumulative damage refers to fatigue effects other than constant amplitude cycles, as I said. So, amplitude will not be constant in practice. The amplitude will keep varying on the machine components, that is, amplitude of loading, keep varying. So, the cumulative or collection of such amplitudes is called as spectrum. Okay, in fatigue literature it's called as spectrum. How we get this spectrum? As I said, if you place transducers and accelerometers near the lathe spindle connected to for FFT analyzer, you will get the spectrum of vibrations that are happening on the spindle of or bearings or spindle on a lathe machine when it is in operation. So that is what is called a spectrum, which essentially means a series of fatigue loading events other than uniformly repeated cycles. Could you understand? Now let's look at how a spectrum looks like. Okay. Somebody else. Okay, this is what I was telling about the spectrum. Okay, so that is this is one spectrum, this is another equipment spectrum, this is the third spectrum. This is how you get on your FFT analyzer once you place your transducers and accelerometers on a running machine. Okay, and try to extract the vibrations out of it. This is normally done for studying condition monitoring of machines. That is how the machines are behaving. Okay, that can be studied using by taking such spectrum of vibrations. Are you there? Now, one question is, with this spectrum that we have got on the computer, we know whatever the data acquisition that we do, can we understand anything from this? What can we make out of this? So we cannot really study much with this type of graph. So that is essentially here it says 9.1 shows details to a larger scale. Of course, histories are taken. The load, it can be loads on an aircraft wing or a tractor shovel, not subjected to constant amplitude loading. Okay, so now this spectrum is enlarged and shown here. Is it okay? Details on a larger scale. So from here, we can at least know the maximum amplitude and minimum amplitude in the entire spectrum that we have got from the machine. This is the entire spectrum. This is a small part, or to the larger scale, the spectrum is taken on a larger scale, wherein we can get maximum amplitude that the machine is subjected to and minimum amplitude loading. Okay, that means it is essentially variable loading. Okay, variable loading condition. Are you able to understand why variable loading? Sandesh, why it is called variable loading? Because it is subjected to maximum load and minimum load. It is not constant amplitude cycle, but it is what?
Very.
Variable amplitude loading. Can you see the variable amplitude here? When you join the dots, this is what you are going to get. So this is variable amplitude loading. Amplitude here is different, okay, and amplitude here is different. Is it okay? This is called variable amplitude loading. Are you there? Are you there? So,
Yes, sir.
so more number.
Yes, sir.
Okay.
Yes, sir.
Yeah. Now, how do we measure load history is the next question. So, what methods that can be adopted? To measure the load history, transducers are attached. As I said, transducers and accelerometers. Normally, accelerometers are used for extracting such vibrations on machines. Okay. So, the critical areas of the component are touched, the critical areas of the component. So how do we find critical areas in a component? That can be done by finite element method. So that is using finite element method, what we can do is, say suppose if you have plate with a hole, I think you have done plate with a hole case, which is easy to understand. So this is the plate with a hole. Using finite element analysis, we can find out that around the discontinuity, that is hole, okay, we will have maximum stress, correct? Are you there?
Yes, sir.
Around the hole we are going to have maximum stress. So that is going to be the critical area of the component. So near on that critical area of the component, we are going to mount our transducers and subject the component for loading. Okay, subject the component for loading and then extract the spectrum as we have got over here. You understood what is this FEA? What is the use of FEA here? Finite element analysis is used to identify the critical areas, then use transducers and accelerometers on those critical areas, then take the load history, which will essentially give you a spectrum, something like this. Are you there? Are you
Yes,
there?
sir.
Okay. Are you able to follow me?
Yes, sir.
Okay. So
Yes, sir.
the acquired data from transducers are usually recorded and stored by a computer. Okay, all these can be extracted into our laptops. So the recorded data may be filtered to isolate primary loads, noise, and are summarized to simplify the fatigue damage. That is, using certain filters, that is, frequency filters or what you call high frequency filters, band pass filters. We can use such filters and eliminate unwanted frequencies and keep only those which are required for our analysis. Are you there? Are you there? How a spectrum is obtained? Could you get the clarity? Yeah, could you get the clarity?
Yes, sir.
Can someone please comprehend what I said in how do we get this spectrum? Someone please summarize or comprehend.
If we take a plate with a hole, for example, uh, using finite element, we place the transducers in the critical areas. Uh,
Ah,
After the load is applied on those critical area, we will get the ampli-
we'll get the
amplitude,
we'll get spectrum.
variable amplitude.
We'll get spectrum of loads.
Okay.
Okay, so that will essentially give us the variable amplitude loading. Is that okay? Okay, so the understanding of fatigue life of a machine or a component when it is subjected to such spectrum of loads. That means spectrum of load means normally a series of fatigue loading events other than repeated cycles or other than constant amplitude cycles. This is a constant amplitude, okay, whereas this is variable amplitude. Could you understand the difference between these two now?
Yes, sir.
Are you able to understand? So to get the spectrum like this, we need to use we identify critical areas in a component using finite element analysis, and then using transducers and accelerometers, we are going to measure load history of the component, and then we are going to get spectrum of loads like this. Is that okay? Are you there?
Yes, sir.
Okay.
Yes, sir.
So we'll move on to the next. Now coming to damage quantification and concepts of damage. So fraction and accumulation. So here one approach to variable load history uses the concept of damage. Okay, damage defined as the fraction of life used by an event or a series of events. These fractions are added when their sum reaches to 1 or 100%, we expect and predict failure. So this is what is the effect of damage. That is, I'll give you an analogy. So to approach variable load history, we can use concept of damage. Okay, fraction of life is used up by an event or series of events. That means, say suppose if a healthy person is attached with a damage in the form of high blood sugar or high blood pressure, okay, or high sugar or high BP, what will happen? Fraction of his life is used up by the event of high BP, correct? Or high sugar. Are you there? Are
Yes,
you
sir.
there? These sugar levels, okay, will get, and BP levels will get added up, okay, and it will further damage various parts of the body. That means it will damage kidneys, retina, okay, and heart also. Finally, failure will occur for the person. Correct? Are you there? Are you
Yes, sir.
there? So,
Yes, sir.
getting high sugar or high BP is a damage or an event. These events will continue to eat away other parts of the body, and then when these fractions reaches 100%, we can predict that the failure is going to occur. That is, once a person gets high sugar, kidney failure, eye failure, everything, heart failure, all things happen, and we can predict failure to occur. Similarly, for machine components also, if there is a presence of small crack, so presence of small crack is an event. If this grows further and further, and once it reaches 1 or 100%, then we can predict failure of that component. Could you understand what it is now? What this damage is all about? Yeah? Could you understand?
Yes, sir.
Yes, sir.
Okay. Now, after a crack has been started, one can define damage by the growth of that crack. So naturally, when there is a presence of crack in the component, okay, that crack will go. So at what speed, at what pace this crack is growing, we will be able to predict failure. If the event produces zero crack growth, then it will cause zero damage. If the event causes a small crack, it can lead to a bigger damage. That is, a loading event that extends the crack by 0.01 mm would cause damage which might be defined as D. That is, damage D is equal to delta A by delta AC, where AC is the crack length for the highest expected load and D is damage fraction. However, the same loading event that produced 0.01 millimeter crack growth at an early stage can produce 1 mm crack growth at a later stage. Okay, that is the for 5 Newton load, if it is able to produce 0.01 mm crack in the beginning, the same 5 Newton load can produce 1 mm crack at a later stage. This is what is damage quantification and concept of damage. So here we have got that is the most common measure of damage is the life fraction or cycle ratio, and this is quantifying measure. Okay. So cumulative damage theory as proposed by Palmgren and Miner, linear damage rule. So this is asked almost in every exam, in every question paper. Palmgren Miner linear damage rule is asked. So anyway, before going to that cumulative damage theory, so we have understood what the damage is and what it can do to the component. Are you there? Are you there?
Yes, sir.
So now what
Yes,
we
sir.
do is just note down the term, okay? This often means series of events other than. So please note down this much. You better note down the entire thing. You note down the entire thing so that it will be there for some time in your memory. Please note down the entire paragraph and note down these two sketches also. Okay, this is constant amplitude cycle, this is variable amplitude cycle. Is that okay? Please note down both sketches. Please note down. Okay, note down both the sketches. After completion, all of you please say yes. We'll go further. Finished, huh?
No.
Okay, okay.
Yes, sir.
Finished, huh? Okay. Now next what you do, you please note down this much. That is to measure the load history, transducers, and here you add accelerometers also, transducers and accelerometers. Okay, that is ACCE accelerometers. Okay, to measure the load history, transducers and accelerometers are attached to the critical areas of the component. These critical areas are often identified either analytically or FEA or experimentally. So this acquired data are usually recorded and stored in a computer. Because for your fourth semester project, you may have to do all these things. That's why just I am trying to highlight this portion a little more. Okay, if you are doing your project on some condition monitoring of machines or something like that, so there it will be of greater. Or if in future if you are doing some PhD work on machine condition monitoring, bearing condition monitoring, something like that in your doctoral work, this initial portion will definitely help you as to what condition monitoring is all about. So for that sake I am highlighting this here. Okay.
Yes, sir.
Just note down this sentence. Finished, huh?
Yes, sir.
Finished writing?
Yes, sir.
Yes, sir.
Okay. So immediately after that, please note down this. The loads on an aircraft wing or a tractor shovel are not subjected to constant amplitude loading but are subjected to variable amplitude loading. Please note down this sentence. See, the purpose of making you to write is to have feel of these words. Okay? Because next when you open this, you may not understand much. So if you write once, it will be there in memory somewhere. It will come back after some time, whenever you need. Okay? Please write this sentence. The loads on an aircraft wing or a tractor shovel are not subjected to constant amplitude loading but are subjected to variable amplitude loading. If you are finished, we will go further.
Finish, sir.
Finished? Okay. Next is to one approach to variable load histories uses concept of damage defined as, you just write damage is defined as the fraction of life used up by an event or series of events, and these fractions are added, and and when their sum reaches 1 or 100%, then we can predict failure to occur. So start from damage and complete the sentence in your notebook. Damage is defined as the fraction of life used up by an event. Damage defined as the fraction of life used up by an event or series of events. These fractions will add up to, when their sum reaches 100%, we can predict failure. Finished, huh?
Yes, sir.
Okay. Next, come to the last. Take D is equal to delta A by delta A by AC. Delta E is small change in crack length. AC is the crack length for the highest expected highest expected load, and D is the damage fraction. Just note down this. D is equal to delta A by AC. So AC is the crack length for the highest expected load, and D is damage fraction. Just note down that much. We are in damage quantification and concepts of damage. Okay, shall we move on?
Yes, sir.
Okay, yeah. Now, coming to cumulative damage theories. So, the most important is Palmgren minor linear damage rule. This is repeatedly asked in all the examinations. So, please concentrate on this more. So the according to this, the damage caused by one cycle is defined as D is equal to 1 by NF. What is D stands for? D stands for damage fraction. And NF is the number of repetitions of this same cycle that equals the median life to failure. So the damage produced by n such cycles is then given by nd is n into d is equal to n by n number of cycles, nf. Is that okay? So according to this rule, Palmgren-Minor rule, okay, so the damage caused by one cycle is defined as d is equal to 1 by nf, where nf is the number of repetitions of the same cycle that equals the median life to failure. Okay, number of cycles that leads to failure. So the damage produced by n such cycles is then n into d is equal to n by nf. So, and figure shows two blocks of constant amplitude stress cycles and corresponding SN curve with fatigue lives at stress amplitudes of SN1 and SN2 denoted by NF1, and NF2 is the number of cycles. The damaging effect of N1 cycles at SN1 stress amplitude is N1 D1 is equal to N1 by NF1. Similarly, for N2 cycles, it's going to be N2 D2 is equal to N2 by NF2. So that is what the damaging effect of N2 cycles is given by N2 D2 is equal to N2 by NF2. So this is what he says. So this is N1 is the number of cycles that is subjected to a constant amplitude, and then N2 is another number of cycles, okay, that is NF2, for which the stress is lesser. So the number of cycles subjected to lesser stress, and these are the number of cycles that are subjected to higher stress values of SN1, and this is their SN curve. That is essentially the title goes that it is constant amplitude stress blocks. Okay, SN1 is one stress block, SN2 is another stress block, but SN1 you will have constant amplitude stress block, SN2 will have another constant amplitude stress block. Is that okay? From there, whatever the SN curve that we obtain is the SN curve as shown in figure B. Now what you do is, please note down this, okay, the entire Palmgren minor linear damage rule, and next we'll go to the sketch that we are going to take. Okay, note down this Palmgren minor linear damage rule. It's very repetitive in all the examinations. Note down the entire thing. Please note down that as a very important one, Palm-Grain minor linear damage rule is very, very important from examination point of view also. Did you finish? Mithun, over?
Yes, sir. Finished, sir.
Okay, then take the next one. Note down this. It is constant amplitude stress blocks and a sun curve. Okay. So A is constant amplitude stress blocks. B is SN curve. Write down this also, that is N2 D2 is equal to N2 by NF2, because next equation is going to be based on that only. Finished, huh? Finished?
Yes, sir. Yes, sir.
Okay. So just before we go to the next one, probably there's going to be a problem. We'll recap what we learned today. So we learned that the cumulative damage refers to fatigue effects of loading events other than constant amplitude cycles. And spectrum, as used in fatigue literature, means that series of loading events other than uniformly repeated cycles. Then we learned as to how I can identify critical areas either by using FEA or the experimental method, and then we can measure load history by using transducers and accelerometers, and all the data can be extracted into a computer. Okay, and then we learned about what a damage is. It is a fraction of life used up by an event or series of such events. When their sum up reaches 100%, then we can expect failure of the component. Then we learnt about damage fraction given by delta A by AC, where AC is the crack length for the highest expected load and D is the damage fraction. Then cumulative damage theory, one of the most important cumulative damage theories is given by Palmgren and minor linear damage rule. According to this, damage caused by one cycle is defined as D is equal to 1 by NF, where NF is number of repetitions of the same cycle that equals life to failure. Okay. So when n such cycles are produced, damage is produced by n such cycles, then n into D is equal to n by NF. This is what we learned. And then we learned about constant amplitude, stress blocks, and SN curve. Okay. So in the next class tomorrow, very important. So we'll go through what is the minor rule, and then we are going to take up one problem based on that. Is that okay? Are you there? Did you get the clarity?
Yes, sir.
Okay, then. So we'll see tomorrow or day after tomorrow for the class, and we'll continue with the Palmgren minor rule. Is that okay?
Okay, sir.
Fine. So all of you hope received your PPTs.
Yes, sir.
Yes, sir.
Yes, sir.
Please keep studying. For second internals may also be online, so be prepared. Okay.
Okay.
Yeah, and convey it to your friends also.
Okay, sir.
Okay. Okay then. Bye.
Thank you, sir.